Okay, we're back in chapter 7 for part 2. So we've been talking about kinetic energy. We've talked about collisions also. So a collision in which your kinetic energy is conserved is known as an elastic collision. Now, the kinetic energy is not going to be conserved at all times during the collision, but the total kinetic energy after the collision is equal to the kinetic energy before the collision. Anytime you have a collision in which the kinetic energy is lost, that is known as your inelastic collisions. Most collisions are inelastic. Some of your kinetic energy is converted to other forms of energy, primarily in the form of heat. So whenever you have a collision where the objects move away with a common velocity, they're never elastic. So in all your collisions, momentum is conserved if there's no net outside force. So when a force acts for a certain time, the force is going to produce an impulse that changes the momentum of the object. The distance through which the force acts determines how much kinetic energy is going to change. So the product of the force in the direction of motion and the distance moved is known as work. We use a capital W to signify work. So work is force times distance as long as the force in the direction of motion. The units for work are the same as for energy, a joule. If you're using the English system, it would be a foot-pound. We do have a special case of work against gravity, and that's going to apply when an object is lifted, because whenever you lift an object, you're doing work against the gravitational force in order to move the object. So to determine this type of work, we have to use the weight of the object. Okay, so for this type of work, your force, your gravitational force, is your weight, and weight equals mg. Notice weight is our lowercase w. So the distance moved, upward or downward, is going to be this formula. Work is mgh. Okay? Mg is your force, which is the weight. H is the amount you've moved it up or down. So anytime you're moving something horizontal, it's going to be work is force times distance. Anytime you move something vertical, it's going to be work equals mgh. Okay, let's do some problems. So a horizontal force of 25 newtons, so we have our force is 25 newtons, pulls a box along a table. How much work does it do in pulling the box 80 centimeters? So our distance is 80 centimeters. Now you have to think, what formula should we use? Well, it's saying horizontal. It's not telling us it's lifting something or up or down. So then we're going to use the formula work is force times distance. But remember, our units have to be a joule. So the only way we're going to get a joule is to convert the 80 centimeters. So 80 centimeters equals 0.8 meters. So our work is going to be our force, 25 newtons, times our distance, 0.8 meters. So our work will equal 20 joules. Now you might remember that we said a joule was equal to a kilogram meter squared per second squared. And now in this equation we have a joule being a newton times a meter. Well, if you remember, a newton equals a kilogram meter per second squared. Okay, so you have this times a meter, which will give you a joule equal to a kilogram meter square per second squared. So you can see a joule equals a newton times a meter, or you can write it as a kilogram meter squared per second squared. Okay, a horizontal force of 100 newtons is used to push a 20 kilogram box across a level floor for 10 meters. So we have our force is 100 newtons. We have our mass is 20 kilograms. We are given our distance is 10 meters. How much work is done and how much work is needed to raise the same box by a height or by 10 meters. So H is 10 meters. So work done in part 1, work is going to be force times distance. So my force is 100 newtons. It's moving a distance of 10 meters. So my work is going to equal 1,000 joules. Now the second part, I'm raising the box, so my work is going to be mgh, which is going to be my mass, 20 kilograms. If you remember, lowercase g is our constant, which is 9.8 meters per second squared, times the height is 10 meters. So our work is going to be 1,960 joules in that case. Oops. Now, Newton's second law and our expression for acceleration and distance traveled can be combined with the definition of work to show that the work done on the object equals the change in the kinetic energy. Okay, so work done on an object equals the change in kinetic energy. The net force is in the same direction as the velocity, the work's positive. Your kinetic energy is going to increase. If the net force and velocity are oppositely directed, the work is negative and the kinetic energy is going to decrease. Okay, this ends part 2 of chapter 7.